All right, this last little section about solids has to do with the bonding within solids and melting and boiling points and things like that. So when we're talking about solids, there's actually 4 different types of solids. It depends on what kind of bonds are in there. And again, then what type of intermolecular forces are in there. So there are what are called molecular solids. Molecular and covalent are kind of synonymous. So anytime you have a solid that is made of a covalent molecule, like ice, carbon dioxide, solid carbon dioxide, rubber is a molecular solid. Their molecules have relatively weak intermolecular forces, so they have relatively low melting points. They are very poor conductors of electricity. Now you might be like, I thought you were telling me that water, which has hydrogen bonds, has a high melting point. So, well, for covalent substances, it does, but in general, it's pretty easy to melt water compared to things like salt. Or any other types of like things that are solid at room temperature. So a covalent or molecular solid is always going to have a relatively low melting point, like room temperature, or maybe you just got to heat it up a little bit. Glucose would also fall under this category. Okay. Ionic solids are the another type of solid. So this is like covalent bonds. These are things with ionic bonds because melting things that are ionic is very, very difficult. Have you ever melted salt? Probably not. You've probably burned it. NaCl is something that's really hard to melt. It melts at an extremely high temperature because when you try to melt ionic solids, you're actually trying to break those ionic bonds, and that's crazy hard to do. So the ions are held together by those ionic bonds. They have high melting and boiling points. They actually have large unit cells because there's 2 ions. So if you're taking into account all of the ions, that unit cell is actually quite large. They are hard and brittle because of these unit cells. If you break it, you're actually breaking it along the axis of a unit cell. So that's why they like crack and break instead of just smooshing or anything like that. And they can only conduct if they're dissolved or melted because those ions need to be able to move in order to conduct electricity. In order to conduct electricity at any point for anything, you have to have moving charges. So ionic solids can't conduct electricity, but if they are dissolved or melted, they can because the charges can move. So these are the properties for covalent or molecular solids and ionic solids. There's actually 2 more types. You might be like, well, we talked about covalent bonds, ionic bonds. What about metallic bonds? Okay, things that are metallic, oh, I'll get back to that in a minute. Things that are metallic like copper or aluminum. Those are held together, as we know, by a sea of electrons. They're great conductors and they have high melting points. They are malleable and ductile because when you smash them, that is, they just smash. They don't have those unit cells that break. Okay. Now, what was I doing up here? Sodium chloride is a unit cell, and another in the body center. Oh, I won't have you do one of these. This was just like how big is the sodium chloride unit cell. You would kind of want to draw it and figure out. The unit cell has sodium ions on each edge, so that would be like 1/8 for each corner of the unit cell, and another in the body center. So 2. Oh, edge. Sorry, edges we talked about a while ago. It's on the edge. You get a 1/4 of it. So a 1/4 times 12, there's 12 edges in a cube, would be 3 plus the 1 in the body. So there's 4 sodiums. And then the chloride ions are found on each face and at each corner. That would be 4 chloride ions. So there's 4 of each in each unit cell. This is a different type of unit cell that we haven't talked about. So that was just an example. Again, that's why they get those brittle consistencies. So we did covalent, metallic, and ionic. What is the 4th type? We don't have a 4th type of bond. And you're right, the 4th type is actually a covalent type, but a very special covalent. They're called covalent network solids. These are non-metals, right? Covalent bonds, but they're atoms that actually, when they're held together, they have a 3D network, which makes them very hard to break up. So they're very special covalent molecules. For example, this is one that has like a 3D structure. So they have abnormally high melting and boiling points for a covalent substance. So if I give you a covalent substance and you're like, oh, well, it's like CO2, it's covalent. CO2 is a poor example because it's not a covalent network solid. But if I told you that its melting point was like 500 degrees Celsius, you'd be like, that's really high for something that's covalent. So it's probably a covalent network solid. Examples of this include diamond, which is just carbon, right? A bunch of non-metals. Diamond actually has a 3D structure, so it has a super high melting and boiling point. So it is considered a covalent network solid, a special type of covalent solid. Graphite is the same. It's hard to melt graphite because it's got a 2D structure at least. Those are called allotropes of carbon. Silicon dioxide. This is actually what's in sand particles and glass, right? Sand can be made into glass. Silicon dioxide, if you look at that formula, that's covalent, should have a low-ish melting and boiling point. What actually is very high, right? To melt glass, it has to get very, very, very hot. And that's because silicon dioxide is a type of covalent network solid. Also, these are really cool. It's called a buckyball. You've probably seen a toy ball like this. These are actually things that chemists have made. It's a bunch of carbons bonded together in this really cool 3D structure. It's called the covalent network solid because of its 3D structure. So anytime you notice something that has a very high, unusually high melting point, but is a covalent compound, it's a covalent network solid. Ones you should know are carbon and silicon dioxide. Okay, so comparing melting points of solids, if I said, which one do you think is going to have the highest melting and boiling points? What I want you to first of all figure out is what type of solid is it? Is it molecular, covalent? And if it's covalent, it could be molecular or a covalent network solid. So you got to check, is it carbon or silicon dioxide? Does it have a super high melting point? If not, it's probably just a molecular one. If it's a metal and a non-metal or a polyatomic ion, it's ionic. And if it's just metals, it's metallic. So these are going to be the lowest melting and boiling points, molecular. And then you're going to have ionic, and then it'll be metallic. Metals have really high melting points, right? And then covalent network solids. So this will be lowest, and these would be highest. Now, what if they're the same type? What if I'm comparing two molecular solids or two covalent network solids? If they have the same type, I'm probably only going to do this for molecular, ionic, and here we go, metallic, covalent network solid. Oh no, I did all four of them. Okay, so if they're both molecular, so they're both going to be low, but then it's based on intermolecular forces. Does it have hydrogen bonding like water? It's probably going to be higher. Is it nonpolar like methane? It's probably going to be lower. So you need to look at the intermolecular forces. Now, if they're all ionic, this is one we've actually talked about before, it depends on the lattice energy. Because when you're trying to melt an ionic compound, you're actually trying to break up that lattice. So things with stronger charges are going to be harder to melt. So we would assume that magnesium oxide has a higher melting point than sodium chloride because it has stronger charges. If they're both metallic that you're comparing, it depends on the number of unpaired electrons. More electrons can move around those delocalized electrons, the valence electrons, or unpaired electrons. It's a stronger metallic bond. And if they're both covalent network solids, well, they always have high melting points. I'm not going to have you try to determine, for example, quartz melts at about this temperature and diamond melts at about this temperature. There's no way for you specifically, based on what we've learned, to know which one's going to be higher. Okay, so in example number 10, I said for each of the pairs, decide which will have the higher melting point. So again, check what type they are. And then if they're the same type, you got to compare based on what we were just talking about. Okay, so I got manganese and zinc. These are both metals, so they're both metallic. So we got to look at the unpaired electrons. So I drew out their electron configurations. Well, manganese has a lot more unpaired electrons. It's going to have a higher melting point. Silicon versus CH4. These are both just covalent things. They're molecular compound, molecular solids. So it's based on their intermolecular forces. Well, they're both nonpolar, so they both only have London dispersion forces. And when we were talking about London dispersion forces, we said if they are bigger, higher molar mass, more electrons, they're going to have a higher melting point. So CH4 is only 16 for its molar mass, whereas silicon is 28. This is actually going to have a higher melting point. So that kind of goes back to when we were talking about London dispersion forces. KCl versus CaO. These are both ionic. I got to look at the charges. Well, CaO is +2 -2. It's going to be higher lattice energy. And these two are both molecular, NH3, PH3, both covalent compounds. They're covalent molecular solids. They are not covalent network solids that we know of or had to know. So which one's going to be higher? Well, which one has the strongest intermolecular forces? Well, NH3 has hydrogen bonding, so it's going to be higher because it has hydrogen bonding. And that's it.